Hi guys, what I want to do today is go over plate tectonics. So our standard that we're trying to hit, we're trying to construct an explanation of how the movement of lithospheric plates, called plate tectonics, can cause major geologic events such as earthquakes and volcanic eruptions. So before we talk about plate tectonics, let's review something really quick. What we're trying to talk about is scientific theories. So plate tectonics is a scientific theory, and what we're trying to do is explain something that happens in nature. We're trying to explain something that happens in nature. And in order to be a scientific theory, it must have evidence. So plate tectonics is supposed to provide the evidence, for its idea. So plate tectonics is a theory. Again, a theory attempts to explain why things happen in nature. It attempts to explain things that we see happening in nature. So what are the types of things that it does attempt to explain? So there are two main things that plate tectonics attempts to explain. The first is continental drift. This is something we talked about. This is the phenomena that we know that the continents used to be together and form Pangea, and now they have spread out and they have drifted into their positions. And the second thing that plate tectonics aims to explain is the concept of seafloor spreading. So we're going to talk today about what is seafloor spreading. So remember what we talked about already, what continental drift is. In 1910, a man named Alfred Wagner proposed that one time the continents were joined together, but over time they have moved slowly into their current locations. So his theory is called continental drift. And remember, what we're trying to use is plate tectonics to explain his theory of continental drift. But let's review continental drift theory. So remember, Alfred Wagner described that all of the land masses on our planet, the continents that we see, Africa, North America, Europe, Asia, Australia, even Antarctica, were once collected together into a solid land mass, or one single continent, a supercontinent. And he called this landmass Pangea. Pangea for all Earth. And so there were some pieces of evidence that he used to prove his hypothesis that all of the continents were together. And remember, these are the pieces of evidence that we talked about. This is what Pangea would have done over time. So let's watch this short animation of what our planet looks like today and how it came from this supercontinent right here that we see. It's Pangea. So this is our Pangea. And this is what happened over time. Okay, and so there were a couple pieces of evidence that we've already talked about for continental drift. The first piece of evidence that Wagner proposed was that all of the continents seem to fit together like a puzzle. And so where this might be modern day Florida, this might be modern day Colombia, and this might be modern day Botswana in Africa. You can see here, these continents all kind of fit together into a supercontinent of Pangea. The second piece of evidence that he noticed, that we find the same fossils that have been found across continents. And so you can see there's this fossil of a prehistoric reptile that is a walking animal. So it has legs it would not have been able to traverse this great distance of the ocean, and therefore these continents must have been together. That was the second piece of evidence. Remember, we talked about the glacial deposits that we find in these much warmer continents. So this is South America here, in Southern Africa, even into India and Australia. And we only find glaciers now on the poles, so in Antarctica. And therefore, we know that these glaciers must have formed a long, long time ago, back when these continents were more near the poles. So these continents must have migrated north from our polar regions over a long period of time. And we find these glacier deposits, or these scratch marks where glaciers used to have been. And so this is just a representation of kind of how we might have predicted the puzzle piece to kind of form together over time. This is a song by the Amoeba People. I'll let you check this out on your own on the slideshow. But this is just a short song that kind of brings into light that Alfred Wagner was not accepted in his time. He was not accepted because he lacked evidence. And so it wasn't until much later after his death that the continental drift theory was accepted, and this concept of Pangaea as a supercontinent was accepted by scientists. And thus, the next theory we'll talk about is the idea of seafloor spreading, which is the second piece of evidence to our to our plate tectonics theory. So plate tectonics will aim to explain seafloor spreading and continental drift. So what is seafloor spreading? Well, in the 1950s, Marie Tharp was a geologist, and using sound waves, she began to map out the ocean floor. She was a woman, and she was not allowed to go onto the boats to conduct research, so she sent her lab partner to do it. And the lab partner brought the data back from the sound wave data, and they were able to map the seafloor from the sound wave data. And using this data, they were able to map out the bottom of the ocean, where they discovered a mountain range that is now known as the Mid-Ocean Ridge, or the Mid-Atlantic Ridge. And you can see it right here. It runs all along the Atlantic Ocean in between Africa and South America, and North America and Europe. Now, this is the longest mountain range in the world. It circles the globe like the seams on a baseball, connecting all of the oceans. So it connects the Indian Ocean to the Atlantic Ocean. And now, how do we know, or how did these mountains form? How is a mountain forming underwater? So the concept of seafloor spreading, this is a theory that states that two pieces of oceanic crust, meaning underwater crust, under the ocean, crust being the top layer of our planet, on either side of the mountain, so on both sides of the mountain here, they're pulling away from each other. These two crusts are pulling in opposite directions away from each other. And this is creating a deep, deep crack all the way down to the mantle. And in the mantle, this is where the lava or the magma within Earth's core rests. And this magma will slowly come up underneath, seep out of this crack, and it'll begin to cool. As the magma comes out, it hits the cold water of the ocean and instantly cools and hardens into rock. And as this process continues, the old seafloor is getting pushed out towards the continents, while the new seafloor is being created at the mid-ocean ridge. So let's look at this image here. This mountain is forming underneath the ocean, and all of the new rock, or where the lava cools, it is forming to the youngest rock right here. The youngest layers are forming right here in the middle. And over time, as they get pulled apart, we find the older and oldest parts of the seafloor have spread out the greatest distance from this ridge here. And so we find the youngest in the center and the oldest on the outside. And so this explains seafloor spreading. So now we understand what seafloor spreading is. This is what we have found underwater. And now we have talked about continental drift. Let's see if you guys can theorize now. How is it possible for these two things to happen? How might plate tectonics explain seafloor spreading and explain continental drift? So we'll pick this up. How is it possible that these plates here, these oceanic plates, why are they pulling apart? Why would that be happening?